SAC107 number 2. You've got two cars, car A and car B, and they're moving toward each other on a straight road. Initially they're 240 meters apart, and car A is moving to the right. So I'm going to put car A over here. Car B over here. Car A is initially moving to the right with a velocity I'll call VA, 0. And so VA at time 0, and it's moving to the right at 28 meters per second. And let's get the x-axis indicated, and xb at time 0 is given as 240 meters. Alright, let's read some more. Car B is moving leftward at 12 meters per second. I know it looks a little strange, but I'm going to put that on there as car B has a rightward velocity that I'll call VB0, but it's equal to negative 12 meters per second. So a negative value assigned to a rightward velocity means that the object is actually moving leftward. And it's convenient to keep everything positive to the right, and so I want to define VB0 as being positive to the right. So the value that it's got is thus negative. And then the velocity of car A remains constant, so VA for all time is at 28 meters per second, but car B has a steady acceleration of 15 meters per second squared. Now, when someone just says a car is going this way with this speed and an acceleration of 15 meters per second squared, that means that they're speeding up. When it says that the car is accelerating, it's accelerating in the direction in which it's going. So it's going leftward, and it's got an acceleration of 15 meters per second squared. That corresponds to a rightward acceleration, I call it AB, of minus 15 meters per second squared. So common understanding of the English language, somebody says the car is going this way and it's got an acceleration of 15 meters per second squared. It means it's accelerating in the direction it's going, which is leftward, which is just the opposite of the direction that I've chosen to define to be my positive direction for A sub B by drawing this arrow to the right and labeling it A sub B. So it's got a negative value of rightward acceleration. Now, when do the cars pass each other? I write down the collision equation. They pass each other when XA is equal to XB. So this is the collision equation by definition. When XA and XB are equal, they are passing each other. So let's write down an expression for XA that's good for all time. XA, there's no acceleration, and it starts at position 0. So XA is just, well, let's write down the whole position equation for the case where there is some acceleration. We'll scratch out the terms that don't apply. So VA0t plus 1/2 A sub A t squared. And then the pieces that cancel out, it starts out at the origin, so that would be a 0. And this term cancels out because A sub A is 0. There is no acceleration. And hence, XA, valid for all time, is just VA0 t. Now, so far we can look at this as a parenthetical remark with respect to this statement. I now have an expression for xa that I can plug in to that expression. Xa is equal to xb. Our expression for xb similarly would be xb0 plus vb0t plus ab, 1/2 ab times t squared for constant acceleration equation. I think of that as constant acceleration equation number 1. And this ends our parenthetical remark. Now xa being equal to xb means that va0t is equal to xb0 plus vb0t plus 1/2 a sub b times t squared. Now all I have to do is solve that for t. I note that I have a t squared, so I'll probably have to use the quadratic. Let's start arranging it in the form of the quadratic equation to see if I really need to use the quadratic formula. So I'm going to rewrite the right-hand side here, 1/2 ab t squared plus the vb0t, but I'm going to subtract va0t from both sides. So that leaves vb0 minus va0 for the number of t's that I'm going to have on the right-hand side, and then plus xb0 equals 0. Solve that for t. I've got t. It's going to be equal to minus this. So I think I'll write that as va0 minus vb0 quantity squared. That's the negative of b, plus or minus b squared. I'm going to write it in the same order, just makes it easier for me to evaluate. And I've introduced a minus sign, but minus 1 squared is 1, so I can write my b squared this way. Of course, that's going to be under the square root. Minus 4 times a 1/2 ab. So minus 4, there's the a term, times c, which is xb0. And then all over the 2 times their a term, 1/2 ab. Now, keep in mind, substitute it rather directly there. I guess I didn't completely follow that rule, but b squared and minus b squared are obviously the same thing, so we're okay there. And minus b, I have distributed that minus sign already. And it looks like I've put a square there, which is erroneous. It's minus b plus or minus the square root of b squared minus 4ac all over 2a. So then t, simplifying, I'm just going to write 4 times a half is 2 and 2 times a half is 1. That's all. The only change I make in this step. va0 minus vb0 plus or minus the square root of that same quantity squared, and then minus 2ab xb0 all over our AB. So now we just have to substitute values from above. We had VA0 was 28 meters per second, VB0 minus 12, and the minus 15 for AB, 240. I don't know if I will remember all of that, but 28 and 12. 28 and minus 12 I should. So we got 28 meters per second minus a minus 12 meters per second. Then plus or minus the square root of that same pair of values squared minus the acceleration, which was 2 times a minus 15 meters per second squared, times the xb0, which was 240 meters. All divided by our acceleration, which was minus 15 meters per second squared. So we substitute those values into the calculator, evaluate, and I get 3.59 seconds, which rounds to 2 sig figs. All our values given to 2 sig figs, to 3.6 seconds as my answer to part A. That's what I've been working on so far, part A. And I want to know, how far does car A travel before passing car B? Oh, I want to mention one more thing. There are always 2 solutions here. I got, this is a positive value. That same value is squared, but then with a double minus sign, I'm adding stuff onto it. So I'll get a negative value for the time when I use the negative, or for the top when I use the negative here, and the negative of that is the one that yields this. If I choose the positive side, both these terms will be positive divided by a negative value. It gives me a negative value for t, which is unphysical. These cars just started moving the way they are, so a value of time that is negative corresponds to the past, and we're not concerned about when they would have last passed each other if they had this same kind of motion historically. So the positive solution is the one that we need. Okay, in part B, we want to know where XA, or car A, is at that particular time. And our expression for XA is right up here. I'll copy that down, VA0 times T. Which is our 28 meters per second times, and I use the unrounded value of time. I can give that as an intermediate result in order to get the best possible value here. And I got written down 100 meters. I want to check on that. I think I've got incorrect value of time when I did it before, so I'll get my trusty calculator out here. And evaluate that expression that we just wrote down. (28) times 3.59 equals, I do get 100.5 actually. I'll call it meters, which to 2 sig figs, I just want to round it to this place, would be 1.0 times 10 to the 2 meters. So 100 meters. And part C probably asks how far car B goes, but let's make sure that's what they want. how far does car B travel before passing car A. Remember, it is actually going in this direction. So I want to find the position at which they pass. They're both passing at the same position, which is the 1.0 times 10 to the 2 meters. And in order for car B to be at that position, it's got to travel a distance leftward of 240 meters minus the 100 meters. So I'll call it XB. Better not call it XB. So distance traveled by B is equal to the magnitude of its initial position, the 240 meters, minus the distance that it traveled there. I'll call that 140 meters, and to make sure that it's clear that it's good to 2 sig figs. That's how far car B traveled. I want to make a quick check here. I am running out of space. XB should be equal to 1.0 times 10 to the 2 meters if part A is right. They both cross at the same position. So XB at that special time, 3.59 seconds. So let's get our expression for XB. We've got up there XB0 plus VB0 T plus 1/2 AB times T squared. Substitute the values. It was 240 meters plus the VB0 was minus 12 meters per second, and then I'm multiplying that times T, which the special time under consideration when this is supposed to yield a result of 100 meters is the 3.59 seconds, the so-called collision time, and then plus 1/2 of minus, I think it was a 15 meters per second squared. I'll check on that. Minus 15, and that was minus 12, which is what I used. 15 meters per second squared times the 3.59 seconds squared. That was a 12 over there. So it'll be a quick check to see if we got that one right. See if that time makes sense. So 240 minus 12 times 3.59 plus 0.5 times a minus 15 times 3.59 squared. And I get 100.259, so I call it 100.3. To too many sig figs, but the point is that it does agree with our position of car A at that time, and indeed they are supposed to both be at the same position. So this was just a check down here. But indeed everything does work. And if at the end of that time interval car B is at 100 meters, and at the start it was at 240 meters, then indeed it did travel 140 meters. I'll mention that, call that leftward. Let's go leftward. So toward the other car or leftward. And I want to make sure that it wasn't I that just, in solving the problem, as the problem solver that made up those. But, yeah, there was a right and a left in the original problem. So that does it for SAC 107, number 2.